Hello, my name is Harris Newstetter. I want to talk about the industrial control landscape and the things that annoy me with machine building and integration currently, and what I would like to see come into the market to kind of alleviate this pain, make my life a little better. So when I talk about industrial control, what I'm talking about is the hardware that we use to control physical things in industrial machinery through code. So think about switching valves for pneumatics, stepper motors, discrete I/O, analog I/O. This is what I mean when I talk about industrial control. So it's how we use code to control the real world for industrial machinery. So I'm going to go ahead and do a little bit of a gripe session where I lay out all the things that annoy me and then my proposed solution to make life better, not just for me, but hopefully other people too. So a little bit of background, I build custom automation machinery for a living. I run my own business and I am gainfully employed. I build machinery every day. But I kind of occupy maybe a weirder spot in the industrial landscape. So if you think about the TV show How It's Made, where you see these giant machines that are doing high throughput work, they're making tons of stuff really fast on a huge industrial line. I don't really make machinery like that. What I do is I build kind of custom one-off machinery for automating highly specialized tasks. It's more like lab equipment. It's kind of this blend between lab equipment and industrial machinery. A lot of it is proof of concept or like research and development work, or we're doing partial automation where we're trying to automate one part of a task for smaller companies that are kind of just moving into the automation world, where they're going from, having humans do everything to trying to automate small things that humans used to do. And it usually requires me to do very high degrees of integration with peripherals that are not standard in the industrial world. So if you think about dosers, electrical stimulators, lasers, kind of these weird pieces of equipment that have to be integrated into an automation process but are not standard automation components. And so what I find myself doing is lots of software, lots of mechanical stuff, and it's usually all controlled from a PC for ease of the software for that high degree of integration I talked about. And usually there's not a real-time control requirement. Look at my notes here. So yeah, I already mentioned it's highly specialized equipment. It's one-off. It hasn't been done before. And a lot of times, because it's kind of this proof of concept work, it's very cost sensitive. So I'm going to go ahead and start off with an example application of the type of machinery that I deal with day to day. So you're going to have to use your mind's eye here, but a customer, and I have to keep it generic because of NDAs that I'm under, but a customer comes and says, hey, we want to automate this task, and what we need to do is we need to take a device and we need to precisely align it with something else and then etch it with a laser. And we want it to run lights out and we want it to be automated. And it's this kind of unique task that requires very, very precise motion control. So you think about a machine like that and you go, okay, well, there's going to be a robot to pick and place the devices onto a very high precision XYZ theta stage. And then to align it optically, we have to use a camera. And then we have to move that entire aligned stage into an area for etching with a laser. So, and also it's got to be not prohibitively expensive so that you can actually get the contract and build this machine. Also, the customer wants live views or saved images of the aligned device. And let's see if there's anything else here. That's about it. So what does a control architecture for something look like when you're actually designing the machine, all the different devices that you have to interface with? So this is going to be kind of your big ticket items here. I'm trying to keep it generic, but you can see that we have maybe a SCARA robot for pick and placing the devices. We have a camera that might have to be somewhat specialized for whatever field of view you're working with. On the bottom in the middle there, you can see that's our XYZ theta stage. We have two stepper motors, and then on the right you can see is our laser, And then you have your more generic I/O. So think like stack light sensors. On the bottom right there is a Venturi vacuum generator for generating the vacuum that you use to pick up the devices with the robot. And that vacuum generator will have I/O as well for if your suction is good or if your suction is bad. And so when you have all of this equipment that's kind of weird, think about the laser specifically. Getting that to work with a PLC is going to be somewhat difficult, but we're gonna run through that anyway. So if you're building a machine, the first thing you usually reach for is a PLC. And I'm gonna lay out my case for why I hate doing that. So number one, PLCs, if you're in America, you're going to be asked to use Allen Bradley a lot. And I cannot stand Allen Bradley. I can't stand Studio 5000. First of all, it completely destroys whatever computer I put it on. The software is just garbage. And if I go back, that laser in this application is going to run off of an RS-232 communication cable. So doing RS-232 comms in Studio 5000 is extremely painful. If you've ever had to do any sort of RS-232 communication with maybe the ASCII card on a compact Logix controller, you'll know exactly what I'm talking about. It's like string concatenation hell, and it's all done in ladder logic. It's extremely painful. And then also, that camera, if it's USB, you're not going to get it to work with a PLC, straight up. If you want to use a camera where on the machine the PLC is the main source of control, it has to be an Ethernet IP camera. Those are extremely expensive, and they're also not fun to use either. So you're going to usually reach for Cognex or a Keyence camera. And then also some of these other devices here, so like the stepper motors, they might run on like Modbus TCP or RS-485 if it has an integrated controller. So the other option, I've used Codesys in the past, but again, Codesys seems to break my computer. It seems to be very unstable. It crashes on me all the time, and I just can't get my head around Codesys. It's not fun to use. And then for Siemens, I'm not European, so I've never used a Siemens controller in my life. They're good from what I hear, but again, you're going to be doing structured text or ladder logic. But my main point to drive home here with the PLC route of controlling sort of this custom lab equipment is it's very, very, very difficult to integrate PLCs with these obscure peripherals. So you're going to be doing a lot of very painful ladder logic code. Some of the peripherals you just can't integrate with at all. And so what ends up happening is you kind of have to have a PC on the machine anyway, and then you have this distributed control where the PLC is handling some of the machine behavior and the PC is handling other machine behavior. If you have a USB camera, you have to kind of distribute where the logic is, and it just kind of falls apart quickly, and it's not fun to do. So for these kind of price-sensitive applications, you either have to spend a ton of money getting everything industrial cameras, industrial sensors, but then, for other things like these high-precision XYZ theta stages, they have their own custom controllers, and unless you're going to get custom stepper motor drivers for that stage and then spend all the time configuring it for the holding current, the steps per pulse, or the pulses per step, the electronic gearing, it's not a great time. So for these cost-sensitive applications, PLCs are not only expensive, they drive the price up, but they're sort of limited in what they can do when you're interfacing with these weird peripherals. The other route, of course, is to just go with all of your control in the PC, which is what I like to do, and then use remote I/O to control your industrial I/O where you can. And the problem with this, of course, is that if you're using remote I/O and controlling it from a PC, your only option is Modbus TCP. That's it. You're never going to get Ethernet IP to work on a PC. If you're doing something like a Python or a C# code base, it's just not going to happen. EtherCAT is completely out the door. You're never going to get that to work. But then, with these remote I/O modules, you're sort of limited in the I/O that they give you. So you're basically only going to get discrete I/O and analog I/O. And the documentation has been not great on them for most of the remote I/O modules that I've used. So you basically just get this giant list of registers that you have to manage in the code yourself. And so the reality of an application like this is your control architecture ends up looking something like this. So you can see right in the middle there is our control PC. You're communicating with an alignment camera over USB. Your robot will have some sort of TCP interface. You have to use these custom drivers for the stage with USB. If you want to talk RS-232 to the laser, you have to have a TCP to RS-232 converter. Your stepper motors, you might use Modbus TCP to communicate with them, and then you will have Modbus TCP to communicate with the remote I/O. So it's just this kind of field bus mess that you have to deal with in your code base. So my ideal world, what I would like to see is a remote I/O platform that is not terrible. So you could have just one single remote I/O master that handles almost all the hardware for you. Now, obviously, you're still going to have to deal with some of the complexities of the real world. So the alignment camera, you're still going to have to talk to over USB. In this particular situation, you'll still have to talk USB to the stage drivers. But the idea is to get as much of the hardware controlled by a common platform as possible. So if you think about this sort of remote I/O, you would have like an RS-232 module for communicating with the laser. You'd have dedicated stepper driver modules, and then you have your typical discrete and analog I/O. And as far as I can tell, this platform does not exist. It's very hard to find remote I/O that solves my problems. And what I would like to see is something that's like an industrial Arduino almost. Now, I use that term kind of loosely, but what I mean when I say that is a remote I/O platform that is very easy to set up and use, and something that allows me to control my industrial I/O from a Python script like that, really quick and easy. I don't want a field bus. I don't want Modbus. I mean, Modbus is great, but I don't want it. I don't want Ethernet IP. I don't want EtherCAT. I want to send plain ASCII text commands to something and control my I/O, as much I/O as I possibly can, through just very simple TCP communication. And that way, that kind of opens it up to control I/O from a bunch of different platforms. You can use Raspberry Pi. A lot of robots have dedicated TCP communication sockets that you can use. Python script, C#, C++, anything where you want to control industrial I/O from a computer. I would like a common platform that makes it easy for me and gives me the most amount of flexibility possible. And what would be even better, sort of like this Arduino platform, if this platform was open source and it was well documented, the community could create custom modules to plug into this common remote I/O platform. So I probably won't end up doing it, but maybe somebody would create a dedicated robot communication module for maybe an Epson, a dedicated robot communication module for a FANUC, a dedicated laser communication module for different types of lasers, dedicated stimulator communication modules, valve bank control, camera modules. There's some pretty powerful ICs out now. Who's not to say that you can't create a module that has a integrated camera that does computer vision for your remote I/O. And the goal of this platform is for it to be as simple and easy to use as possible. A lot of times you get this industrial equipment, and getting it just to turn a single output on is like a day's worth of work. If you have to dig through documentation, there's no good code examples. It is really demoralizing. And then obviously for this platform, you would want it to not be prohibitively expensive. You would want it to be, I don't want to say hobbyist, but it'd be great for small internal R&D applications in businesses to get automation up and running fast, proof of concept type work, and maybe even serious automation work. And then so ideally, we want to, in the perfect world with this remote I/O platform, you plug in an Ethernet cable, and then you can control all of your industrial hardware over a single TCP ASCII text protocol. And so from Python, C#, C++, you can control your whole machine. That's my ideal world. So I have been working on something like this for the past 2 years in my free time when I'm not building machines. I have some demo boards that I've been working on that do work. and I'm kind of going through this process, but I'm calling it FlexCon, which stands for the Flexible Control Platform. And the idea is that you buy a master unit, and then you can chain on up to 16 slave I/O modules. And my goal for this is to have it all be open source and in the public eye, so that we can get some community feedback on it. And the actual remote I/O is based off of CAN FD, which stands for flexible data. That's what's being used in most cars now. And I want this to be, again, as simple and easy to use as possible. So you buy the master, you buy all the I/O slave modules you need, you hook them up, and then you just plug it into a network switch or USB straight to the computer, and then right there from your Python code base, you can control all of your I/O. So as I'm thinking about this and I'm going through the development, some of the expected launch modules that you would want to see if a product like this came to market is you would want discrete combo modules, so maybe like an 8 input, 8 output, dedicated discrete output, dedicated discrete in, RS-232, RS-485, some relay output modules, and then some analog modules. You can do 4 to 20 milliamps, 0 to 24, 0 to 10 volts DC, that kind of stuff. So over the next year, so as I was developing this as a remote I/O module, the thought also came into my mind is that this could also be a low-cost PLC. So for the master unit that controls all the slave I/O, if you used Arduino supported microcontrollers, you could actually just program the master as sort of an industrial Arduino, and then if you had really well-written libraries and documentation for interfacing with all the slave modules, you could just use the master as a cheap PLC for small applications as well. That is something that will probably have to come later, because I'm focusing on the remote I/O aspect of this platform right now. But for the time being, I expect over the next year, I'm going to be developing this remote I/O platform module, and I kind of want it to be in the open. So I'm going to open a GitHub repository and throw all of the KiCad stuff up on there, all the software, all the documentation as I go through it. And so over the next year, I'll also be doing some demonstration videos of the hardware as it comes in. There's going to be a lot of prototyping. As a matter of fact, here I have some of the development boards for Ethernet. This is the input power microcontroller stuff. So I'm going to be getting as much of this into the public eye as I possibly can. And so really just what I want to do is I wanted to lay out my thoughts on this, and then how I'm going to take this from kind of just an idea to hopefully a real product, and what that's going to look like coming forward in the next year. So be on the lookout. I will be posting updates about the development of this platform, and hopefully it'll end up being something good.